So let me only six. Ashutosh, just can you call everyone so they can join before actually Professor Manoj starts doubt clearing session. Because I only see 68 people, right?
So no issue. I think Mohan, we will start. Let us start. Those who wanted to join, they will join in between, isn't it?
That's fine.
Okay.
That's fine. Okay. So thanks, Professor Manoj, for joining for this doubt clearing session.
So hello everyone. Am I visible and audible?
Yes.
Everyone.
Yes.
Okay. Okay. All right. Thank you. So I guess you all of you have done the heat transfer course. So uh, or is there anyone who did not do the heat transfer course?
Most of us did that under you, sir, the previous semester.
Okay, okay. So I don't need to give any more detail, I guess. Or do you want me to give some detail and that will be some starting point for you to ask the questions?
Yes, please give some detail.
Okay. Thank
Yes.
you. I will just briefly describe what is, shell and tube heat exchanger. Anyway, we have done it, extensively in the heat transfer course in the last semester. So I will just present the same slides again. Okay. So just a minute. Let me just open it. So these are the same slides which you probably might have seen in the last semester, isn't it?
Yes, sir.
And you might have also seen the actual shell and tube heat exchanger in the recorded videos, isn't it?
Yes, sir.
Okay. So again to brief you regarding the same, shell and tube heat exchanger is one of the most commonly used heat exchanger in all process applications. Why it is called as shell and tube? Because there is a shell and inside there are different tubes, and one fluid passes through the shell and one fluid passes through the tubes. Correct. Again, you can see here that one fluid is passing through the shell like this and coming in from here and coming out from the other end, whereas the another fluid is flowing in through the tube and coming out from this another end. Okay, so since multiple tubes are arranged in this heat exchanger, in this circular, you can see the disc is there. In that disc there are several tubes are there and these are fixed inside the shell. Okay, so that is why it is called as shell and tube heat exchanger. Okay. Again, there are multiple, shell side fluid is also possible. In this case, I have shown that there are two tube passes and one shell side pass is there. But you can have multiple shell side pass as well. In fact, you might have seen the shell and tube heat exchanger exactly similar to this, isn't it? In your experiment, where there are two tube side passes and one shell side pass, isn't it? Correct?
Yes, sir. Yes, sir. Correct.
Okay. So these are the different parts. So have you tried locating these parts in the shell and tube heat exchanger? So these are the different parts you can, kind of look at in the experimental setup, or at least the lab TA or the lab assistant will help you to identify some of these. The next thing is this I will skip. Okay, so the most important thing is then we have looked at the design of shell and tube heat exchanger, isn't it? So there are two types of commonly used design procedure of shell and tube heat exchanger. One is this LMTD method, and the another one is this effectiveness NTU method, isn't it? Correct?
Yes, sir.
So that is what is written in your lab manual also. Correct. So in a LMTD method, what you do is you first find out the inlet temperature of both the streams, and also you find out the inlet temperature of both the outlet stream. Correct. Based on these temperatures, then you calculate the two factors, isn't it? So you calculate these two factors, tau C and R. Some different names are given in your lab manual, but these are exactly the same, isn't it? The tau C is nothing but the how much is the increase in the cold fluid temperature divided by how much drop is in the how much is the maximum temperature present in the heat exchanger. So that is why it is TH1 minus TC1. Okay, and there is another factor which is nothing but R, or sometimes we call it as a efficiency. So that is TH1 minus TH2. So that is nothing but the how much temperature is increased for the hot decreased in the hot fluid divided by how much increase in the temperature of the cold fluid. Okay, so once you get this tau C and R, based on that you use this plot, and depending on whether it is 1-2 pass or 2-4 pass or 2-6 pass, depending on that you find out the F factor. Okay, so this F factor you find out corresponding to the values of R, tau C, and these individual plots are given for multiple configuration of shell and tube heat exchanger. So it could be for 1-2 pass, it could be 2-4 pass, it could be for 2-6 pass, something like that. So based on the given configuration of your equipment, you find out the F factor, and then you use that F factor in this equation. And based on this you can calculate, you can back calculate what is the transfer area or a coefficient, isn't it? If the coefficient is there, then you find out the transfer area. Okay, is it clear to everyone? This is what we have seen, right?
Yes, sir.
Is it
Yes,
correct, or is there any doubt so far? Maybe I will just again side by side present you the lab report also, so that if there is any doubt with respect to that lab report, you will get it immediately what I'm trying to say here. Okay, just wait. So lab report is also I'm having with me. So this is the lab report, guys. Okay, so here also this is, see, 1-2 pass heat exchanger is what you have looked at in the video. There is 2 tube side passes and 1 shell side pass. Then what you are doing is in the experiment you are kind of noting down these values, temperatures, inlet, outlet temperature, and what is the flow rate. Similarly, for the cold water, you are noting down the values, what is the flow rate, what is the inlet and outlet temperature. Then see how Q is calculated. Q can be calculated. See, in this case, whatever the heat lost by the hot fluid is same as the heat gained by the cold fluid. So you can calculate QH and QC, and both has to be same, but some variation will be there depending on how accurately you are measuring this flow rate. Correct. How accurately you are measuring flow rate or temperature, based on that some variation could be there, and that is why you are taking the average heat transfer coefficient for your calculation. Is it clear to everyone? Hello?
Yes, sir.
Okay, so once you get this average heat transfer coefficient here, also you know what is the inlet and outlet temperature for both the streams, you calculate LMTD, which is nothing but log mean temperature difference. Is it clear to everyone? Hello?
Yes, sir. Yes, sir. Yes, sir.
Okay, so why LMTD is being used? Why not just the temperature difference here? Is it clear to everyone? Why we are using LMTD here and not just the plain temperature difference?
Is varying throughout the system.
Correct. Absolutely correct. Yes. So temperature is varying along the length of the heat exchanger. It's not constant. It is varying from one end to another. Correct. So in that case, if we solve the heat transfer equations, you will finally get that the temperature difference in this case will be accounted by log mean temperature difference, that we have derived also in heat transfer class, if you remember. So once you get this, then you can calculate R and P. Here different notations are there. So here basically this R is nothing but whatever is the temperature, temperature decrease in the hot fluid divided by the temperature increase by the cold fluid. So that is called as R. And this P is nothing but whatever is the temperature increase of the cold fluid divided by whatever is the maximum temperature difference present in the heat exchanger. So maximum temperature difference present in the heat exchanger will be what? Temperature, inlet temperature of the hot fluid and inlet temperature of the cold fluid, isn't it? So that's why it is T1 minus T3.
Yeah.
Okay, so once you get this R and P, then based on R and P, you can find out the F factor, and then you can calculate the heat transfer coefficient. Okay, if you know the heat transfer area. Another way is, okay, so only one part of this, heat exchanger design is given in this experiment, but actually it is beyond that also. For instance, here you might be assuming some value of U, correct? But how U is calculated? How U is calculated in this case? Any thought on that? So U is given in this experiment. Ananya and Anuj, whether this U value is given in this experiment or what? Or A is given?
So we find U first.
Area is given, the
Area is given, U
setup
is you are finding.
length
Okay.
and area is given.
Okay, all right. Thank you. Thank you. Okay. So in this case, the area is given. So length and other things are there. So you can find out the area and you can calculate U. But we can pose this problem differently also, isn't it? Let's say, instead of, looking at the actual experimental setup, if the question is posed like, if you wanted to design the cell and tube heat exchanger, so that means you do not have a heat exchanger with you. So in that case, you need to find out, first you have to find out U and then you have to find out area, isn't it? In this case, since the experimental setup is already there, you already know the value of A, area. Is it clear to everybody?
Yes, sir.
But suppose this instrument is not there and you are, let's say, engineer, and somebody asks you to design a heat exchanger and then order or fabricate that heat exchanger. How you will go ahead? You will use some correlations to find out U first. Then that you will be using in these equations, and then you will find out the area. And based on the area, then you will see how much space is available in your lab, and based on that, you will find out whether it should be 1-2 pass or whether it should be 2-4 pass or whether it should be 2-6 pass. You get it? What I'm trying to say, isn't it? So depending on how much area you are having available, how much floor area you are having available in your lab, based on that you can design your own heat exchanger which can fit into that space. Okay, but that problem we are not solving here. This problem is much simpler. In this problem, the existing heat exchanger is already there, isn't it? And since the existing heat exchanger is there, you already know how many tubes you are having. What is the length of each tube? You can directly find out what is the heat transfer area, isn't it? So heat transfer area, once you get it, your job is to find out the overall heat transfer coefficient U. Okay, so you can use this equation. In this equation, everything is known. You know area, you know the F factor, you know LMTD, you also know Q. You can find out the overall heat transfer coefficient. Is it clear to everyone? Hello?
Yes, sir, it is.
Okay,
Yes, sir.
so maybe I will just give you some more details, and then we have already done these details, guys. In the last, heat transfer course, you have already done this detail. Only thing is that, you need to brush up your concept. That's it. So I will again go back to the same slides one more time. Okay. So this problem is very simple because you just need to calculate the overall heat transfer coefficient and you know everything. And another problem which I was saying, that designing the heat exchanger where you don't know, in that case these are the correlations which you have to use, and then you have to first find out the inside heat transfer coefficient, tube side heat transfer coefficient, cell side heat transfer coefficient, and then based on the shell side heat transfer coefficient and tube side heat transfer coefficient, you calculate the overall heat transfer coefficient. Okay, and once you get the overall heat transfer coefficient, then you go back and calculate the area, heat transfer area, and for the given heat transfer area, then you decide whether that instrument is going to fit in the lab space or not. If it is fitting in the lab space, then it is perfectly all right. Your original assumption is right. If not, in that case, you revisit your original assumption and change it to 1-2 pass to 2-4 pass or 2-6 pass, something like that. Okay, so this is what the procedure is in actual designing. The another point is, okay, so another point is effectiveness NTU method. Maybe I will again ask you one more question. So when the effectiveness NTU method is used, what is the rationale behind even having the effectiveness NTU method?
Sir, it is when we don't know the operating temperatures.
When we don't know the operating temperature, is it correct or some more modification is required in this statement?
So basically it is used when we are designing the reactor,
Sir,
and
when we don't know the final temperatures.
When we don't have the final temperature, that is the correct answer. Yes, you have the inlet temperature. That is because that stream is coming from some other instrument, isn't it? Inlet is coming from some other instrument, isn't it? So that you already know. Outlet temperature you don't know. Outlet temperature depends on how effective your heat exchanger is. Correct. So very often it is possible that you only know the inlet temperature when you are designing the heat exchanger. Correct. And you don't know the outlet temperature. So in that case, you have to use the effectiveness NTU method, because in this method you will see that you only require the inlet temperatures. You don't require the outlet temperatures. Okay, so I will again go back to the effectiveness NTU method and then okay. So as I said that it is used whenever there is only the inlet temperatures are known and the outlet temperatures are not known. How effectiveness is defined? Effectiveness is defined as actual heat transfer divided by the maximum heat transfer. So maximum heat transfer is based on what? Maximum temperature, whatever is the maximum temperature difference present in the heat exchanger, based on that you calculate the Q. Okay, so that is what we have seen. Again, this is how the epsilon is defined, isn't it? Q by Q max, isn't it? Actual heat transfer divided by the maximum heat transfer possible. So again, this Q is what? Q is given as MC TCO minus TCI divided by, or it can be given as MH THI minus THO. Correct. So whatever is the temperature difference of the cold fluid multiplied by the flow rate, that will give you the heat transfer. And similar manner, you can look at the sensible heat based on the hot fluid and you can calculate Q. Correct. But in this expression, remember divided by Q max is there. So Q max is defined in terms of what? It is defined in terms of C mean THI minus TCI. So this is nothing but C mean is what? C mean is nothing but the minimum value of MCCPC or MHCPH. Correct. Whatever is the minimum between MCCPC or MHCPH, that is called as C mean. And remember, this CC can also be represented in terms of C mean. And if this is taken in terms of C mean, then epsilon you can get it in terms of the ratio of the temperatures, temperature differences. So that is what is been given in your lab report. Okay, so I will again go back to the lab report, and then the floor is open for any questions, any clarifications, or if something is not clear. Okay. So let me just So this is what is calculated here. Effectiveness is given as delta T minimum stream. So when I'm saying minimum stream means what? This is corresponding to C mean. Okay, this is corresponding to C mean divided by maximum temperature difference. Okay, so that C mean will get cancelled out here, and we will have delta T corresponding to the minimum C mean stream divided by maximum temperature difference. That will give you directly the effectiveness. Again, this F is the F factor. Don't get confused with the flow rate here. Remember, we have also given here the flow rate FH and FC. These are the flow rate. Don't get confused. These are not the F factor. F factor you calculate from this plot. Is it clear to everyone?
Yes.
Yes, sir.
So now floor is open for any questions. If you are having, feel free to ask.
Sir, can you please like send the observation data to us?
Observation data. So Anuj and Ananya, whether we have supplied this observation data to students or not. Hello?
No, sir, we haven't supplied them.
So what is the problem?
Sir,
So-
actually, I don't have the observation data. Mohan sir can supply it.
Okay, I will just check with that. Hello, Mohan, are you there? So I think lab TA will give. I remember Mohan told me that this will be supplied by the lab. Lab assistant. So lab assistant is available here.
I'm available here. Sir, in this experiment we are using new instruments. So and we have the data from the old experiment. So we can provide that data.
So is it possible to do this experiment again and generate the data and give it to the students? You can supply the old data also, no problem.
We have provided data in a single flow rate, but we can try to take more data in different flow rates. Sir, I hope we have provided in video.
You have provided, but you have not noted down that.
Sir, students can see the data from.
Okay, all right. So does it answer your question? Hello, everyone. Can you kind of see the data from the video? Is it
So
possible?
the data is not complete, sir.
Yes, sir, data is not.
So flow rate is not varying. That is what you are saying, isn't it?
Sir,
yes.
Yes, sir. Heat capacity is also not mentioned. CH and CA.
So heat capacity, if it is not there, remember the fluid is given. Whatever is the inlet fluid and the outlet fluid, that is given, isn't it?
Both are
Hot water and cold water is there. So for this, you can look at the same BK Datta book and find out the specific heat at the backside of the tables.
So, but that is temperature dependent. So
that's what I'm saying. So see, here in this case, you already know the temperatures, correct? Take the average temperature, and at the average temperatures, you can find out the specific heat.
okay, sir.
Okay, sir. Sir, and yeah, the flow rate is not varying.
Flow rate is not varying. Okay. So hello. Who is the lab TA? Mukesh ji.
Yes, sir.
So Mukesh ji, is it possible to provide the data for different flow rates?
Sir, we can run the experiment in next day, but I can provide the data from the old experiment that we are using the steam in the tube side. So I can provide that data for calculation purpose, or we can take more readings for the new experiment.
Maybe you do the new experiment because there you are using steam and here you are using hot water, right?
Okay, sir, we can do that.
So what I can suggest to the students is, if the data is not available, in that case you use the constant flow rate, doesn't matter, because that anyway your aim is to calculate U, isn't it? Correct?
Yes, sir.
Yes, sir.
So it's not going to vary. Okay, if I look at the table, just wait. Okay. So you can calculate Q. Okay, and okay, so one data is there. What you are saying is, but different values of the inlet and outlet temperature data is available to you.
Yes, sir.
Yes,
We
sir.
have provided 4 readings for temperature.
So then doesn't matter. You use the same value of the flow rate. You calculate the Q values for all 4 cases, isn't it? And based on that, you calculate the U value. So you will get this U value for all 4 different data points, and then you report the average value of U. Does it make sense? Hello?
Yes, sir.
See, remember here in this case, each data point will give you a Q, isn't it? This data point will give you a Q. This will also give you a Q, isn't it? Then you can take the average of both these Q, and based on that you can calculate the value of U. Similarly, for the next data point also you can calculate the U. Correct? And finally you will get the average value of U. So Mukeshji, is it correct, or see, this is these values are at steady state or what, or these are varying with time? These are the steady state values you are getting right here.
Sir, we are taking at time equal to 0 first reading, then we are taking readings at time interval of 5 minutes. So
Okay.
So we can do in the similar flow rate, but sir, I can provide the more data in 1 or 2 days.
Perfectly all right. No issues. So once the data is available, you please send it to all the students, students which are there in this course. Okay.
Yes, sir.
Okay. Any other question? Hello. Hello. Any other question? So all are okay. Seems to be really good that you all are okay. Please ask the questions, as many questions possible. Okay. Let me check with Professor Mohan if something is missing, and then so I have checked with Professor Mohan, and he said that you all have to submit the report for this particular experiment by 2 p.m. in the next Wednesday. That is the deadline. Okay, is it all right?
Yes,
So
yes.
I think one link is created in the Moodle, I guess. And if you have any doubt, anything, you can write to Professor Mohan or me or Mukesh ji. Okay. Is it all right? Hello.
Yes, sir. Yes, sir.
So any doubt or anything? Do you need some more clarification, or should we wind up?
Not yet, sir. If we have any, we'll write to you for that.
Perfectly all right, because I think I have taught you, so you will not be able to say that this is not done. At least. All right.
Yes.
Just on a lighter note, I know that you all know. Okay. Okay, then we stop today. And if you have any doubt, anything, you can write me or you can write to Professor Mohan or the lab in charge Mukesh ji. Okay.
Sure. Also, sir, we also wanted your office number because I could not find that on your website.
Office number, I generally do things online these days, isn't it? So my office number is 1026, but if you call there, probably I will not be able to pick up.
Sure, sir. We'll write an email in that.
So you write email, and in general I reply. Unless something which is not in my hand, then I don't reply. But if something is there in my hand, I definitely reply. Okay. Okay, all right.
Yes.
Okay. So can we stop here? Okay, guys, then see you.
Thank you, sir. Good afternoon.
So if you have any doubt, anything regarding this heat transfer instruments or the experiment, feel free to ask. Okay. Thank you. So I am stopping.